Let's get in some more conservation of energy practice, this time focusing on a problem with a change in internal energy. So you build a wall, and the first thing you do is you throw an egg at it. Egg splats, as we'll learn later in the course, you can't use the same egg twice, so we'll put down another egg there that represents the initial conditions of the first egg. It had a velocity vector pointing up this way, and let's say that it was thrown at a speed of 16 meters per second at an angle 45 degrees above the horizontal, and hit the brick wall 4.0 meters above where it was thrown. We're also told that the egg hits the wall without transferring heat or experiencing work. Probably everybody would agree that an egg doesn't transfer an appreciable amount of heat to a wall when it hits it. But what about the question of work? If you think of work as being a force times a displacement, then it seems like this might be a problematic assumption. Certainly the egg felt the force for a little while, after all it was moving and then stopped moving when it hit the wall, and parts of the egg must have been experiencing a displacement while they were also experiencing a force. That would suggest that some work was done on the egg. Well, if it helps you sleep at night, one thing you could do is consider extending the system definition to include both the egg and the wall. In that case, we would rephrase the top question to be, what is the change in the egg-wall system's internal energy? The advantage of that is that now all of the interactions are internal to our system, so certainly there are no external forces doing work on our system and no heat transfer from the outside. We would also suspect that most of the change in internal energy in this system is happening in the egg. After all, it's the thing that got squished. Okay, let's define our z direction to be positive and get started. As usual, the statement of conservation of energy is simply that the change in total energy is Q minus W, and we just talked about how both Q and W should be 0, so the whole right-hand side of that equation will be 0. So delta Ke plus delta P plus delta U equals 0. Let's rearrange to solve for the change in internal energy. We do that and put in the forms for delta Ke and delta Pe. Now we can pull out a factor of mass, bring this up. You may notice before we insert values that unlike the cases where we have conservation of mechanical energy, the mass does not cancel out. So now we actually need to know that the mass of an egg is 50 grams. So we put in that and all of our other values. At this point you should be pretty comfortable with figuring out what the 1 and 2 subscripts correspond to, so I won't walk you through that in great detail. Crunch some numbers and simplify things, and eventually find out that the change in internal energy of our system is 4.44 joules. Not nearly enough to cook an egg, but only enough to heat it up very slightly. Incidentally, you may have noticed that we never used the direction of the velocity, that 45 degree above horizontal bit. That's what's known as an extraneous detail, or a red herring, something that we didn't need to solve the problem. One skill you have to develop in this course is realizing what information you need and what information you can ignore.